Hello there, and a warm welcome to the Science for Sleep channel. I'm truly delighted that you're here with us tonight. Perhaps your day has been long, filled with endless tasks, thoughts, or worries. Or maybe you simply enjoy drifting off to sleep while letting your mind wander among the stars, galaxies, and the quiet, gentle mysteries of the universe. Either way, tonight's journey is designed entirely for you. There is nothing you need to do right now. No obligations, no distractions, no questions to answer. Just allow your body to relax fully, let your mind slow down, and let your thoughts float freely, like tiny motes drifting through a sunbeam. Tonight, we are going to explore the universe itself. Not just a single galaxy, a lone star, or a planet orbiting quietly in the darkness. No, we'll journey into the vast, expanding cosmos, the endless tapestry of space that stretches far beyond what we can even imagine. Our voyage will be gentle and deliberate, moving slowly from one fascinating fact to another, uncovering secrets of black holes, the echoes of ancient light, the invisible presence of dark matter, and galaxies spinning silently in the infinite darkness. Some of these revelations may catch you by surprise, while others may linger softly, like a quiet thought that hovers at the edge of sleep. If you find comfort in these calm, celestial explorations, remember that liking this video or subscribing helps others discover this little haven too. But for now, let us begin gently as we drift together into the mysteries of space. Did you know that the universe might be older than we currently think? Most scientific estimates place the age of the universe at around 13.8 billion years. This number comes from careful measurements of the cosmic microwave background, the faint afterglow left over from the Big Bang, and from the observed rate at which the universe continues to expand. Yet, not every observation agrees with this figure. Some studies of ancient stars and distant galaxies suggest that certain regions may be older than this estimate allows. Other research questions the assumed rate of cosmic expansion, or suggests that dark energy, the mysterious force accelerating the universe, may itself change over time. These tensions remain unresolved, and while most astronomers still accept the 13.8 billion year figure, profound questions remain. Could the universe be even older than we imagine? Could there be something fundamental that we have not yet discovered? Perhaps the moment we think of as the beginning was only one part of a much longer, stranger story. Consider the countless rogue planets drifting silently through space, planets that do not orbit a star. Not all planets are tethered to a sun, warming their surfaces or lighting their skies. Some are completely unbound, wandering alone through the galaxy. These mysterious wanderers may have formed within a star system, only to be ejected by chaotic gravitational forces. Others may have formed independently, as failed stars never fully igniting. They are dark, cold, and nearly invisible, detectable only when they pass in front of background stars, or when they glow faintly in the infrared spectrum. Astronomers estimate that billions of such rogue planets could exist within the Milky Way alone, possibly even more than the number of stars. Each is a silent world, drifting endlessly in darkness, spinning alone across the vast emptiness of space. Imagine their skies without sunrises or sunsets, just the soft glow of distant stars, like whispers across the void. The universe itself may follow a rhythm, recycling through infinite cycles. While the standard model of cosmology describes a universe that began with the Big Bang and may continue expanding forever, some theories imagine a different story. In these models, the universe undergoes cycles of expansion and collapse. It does not end with a cold fade or a final crunch, but instead resets itself. After reaching a certain point, the universe might collapse inward, only to rebound into a new phase of expansion. Each cycle could erase the structures of the previous era, yet preserve subtle traces of what came before. These ideas remain speculative, but they are endlessly fascinating. They suggest a cosmos without a true beginning or end, a vast rhythm stretched across unimaginable spans of time, where one universe gives rise to another over and over again. The oldest light that we can observe comes from roughly 380,000 years after the Big Bang. Before this moment, the universe was an impenetrable fog, glowing with heat and density so intense that light could not travel far without scattering endlessly. But as the universe expanded and cooled, a transformation occurred. Atoms formed, the fog cleared, and suddenly, light was free to move across the cosmos. This ancient light, known as the cosmic microwave background, is still detectable today. It is the oldest direct signal we have from the universe, not from stars, galaxies, or planets, but from the cosmos itself, just as it began to become transparent. The photons we detect now have traveled for more than 13 billion years, stretched by the expansion of space into long, cool microwaves. This faint glow is subtle, ever-present, and quiet, carrying with it the memory of the universe's earliest moments of clarity. Some stars host planets made almost entirely of diamond. In certain star systems, chemical conditions are vastly different from those in our own solar system. If a planet forms with a high abundance of carbon relative to oxygen, and under immense pressure, something remarkable can occur: a planet made of crystalline carbon. Astronomers have discovered at least one candidate, a dense world orbiting a pulsar, likely the remnant of a long-dead star. Based on its mass, density, and composition, the planet may be entirely crystalline, essentially a giant diamond. It is far too hot to sparkle like a gemstone and would not resemble a jewel up close. Yet deep beneath its surface, immense carbon lattices could extend for thousands of kilometers. Such strange worlds are rare, but they remind us of the extraordinary diversity the universe can create. Rocky planets, gaseous giants, and sometimes crystalline marvels. The universe may not have an edge. It is tempting to imagine traveling far enough to reach a boundary, but space does not work that way. According to general relativity, the shape of space is determined by its contents. Current evidence suggests that the universe is either infinite or so vast and curved that it loops back on itself. In theory, one could travel in a straight line forever and eventually return to the starting point, not by hitting a wall, but by following the curvature of space itself. Just as traveling around Earth never reveals a boundary, the universe may work similarly, infinite not in space, but in journey. Our own sun may once have had a twin. Some astronomers believe that our star was born alongside a companion, formed from the same cloud of gas and dust over 4 billion years ago. Many stars form in pairs, and there is no reason to think our sun was an exception. If this twin existed, it would have drifted away long ago, pulled apart by the slow, relentless gravitational tug of the Milky Way. Perhaps it still orbits the galaxy along a different path, unseen by our eyes. Some theories even link this lost sibling, nicknamed Nemesis, to mysterious extinction events on Earth, although no definitive evidence exists. Yet the idea persists, reminding us that the sun, steady and familiar in our sky, may once have shared its birth with a silent companion, now vanished among the stars. Neutron stars are among the most extreme objects in the universe. They are the collapsed cores of massive stars, left behind after supernova explosions. Though only about 20 kilometers wide, a neutron star can contain more mass than our sun. The matter inside is compressed to unimaginable density, so much so that a single teaspoon would weigh billions of tons. Imagine a single raindrop of neutron star material. It would outweigh any mountain on Earth. Atoms are crushed so tightly that electrons and protons merge into neutrons, forming a superfluid soup of dense matter. Neutron stars are small, dark, incredibly heavy, and often spinning rapidly. Within them resides the memory of stellar collapse, a final state where matter exists almost entirely as gravity. Light from distant galaxies can take multiple paths to reach us. Sometimes, light does not travel in a straight line. In regions of space with strong gravity, such as near massive clusters of galaxies, space-time itself curves, bending the trajectory of light like a lens. This phenomenon, called gravitational lensing, allows astronomers to observe multiple images of the same galaxy, appearing as arcs, smudges, or even complete rings. These are not duplicates in space, but duplicates in vision, caused by the different paths light takes through warped space-time to reach our eyes. In rare cases, astronomers have even observed the same supernova explode more than once as its light arrived via different gravitational routes. a quiet, cosmic reminder that even light can wander, take a detour, and still find its way home. The first stars may have burned a million times brighter than the sun. Born from the pristine hydrogen and helium left after the Big Bang, these population 3 stars contain no metals, making them massive, extremely hot, and short-lived. Some may have been hundreds of times the mass of the sun, burning through their fuel quickly, shining millions of times brighter than our star, and ending in spectacular explosions after just a few million years. None survive today, yet their brief lives transformed the universe. They created the first heavy elements, seeded galaxies with light, and laid the foundation for everything that followed, including life itself. Though their light is gone, their fingerprints remain, etched in the chemistry of ancient gas clouds and the quiet structure of the early cosmos. Even now, as you lie still, dark matter streams silently through your body. It is not a ghostly mist, but a form of matter that does not interact with light. It does not emit, absorb, or reflect it, yet it has mass and responds to gravity. Our galaxy is surrounded by an immense halo of dark matter, and as Earth moves through it, trillions of particles pass through every square centimeter of your body each second. They do not collide with your atoms, and they leave no trace, yet they are ever-present, ghost-like, and essential. Without dark matter, galaxies would not hold together, cosmic structures could not form, and the universe would be profoundly different. We still do not know its composition, but one thing is certain. Dark matter is part of your world, flowing through you silently, continuously, even as you sleep. Some galaxies glow without any stars inside them. In the quiet reaches of space, astronomers have discovered ghostly systems filled with gas and dark matter, yet showing little or no evidence of star formation. Some may have lost their stars through violent gravitational interactions, while others may have never formed many stars at all. A few are nearly invisible except in certain wavelengths of light, faint smudges revealed only in deep surveys of the sky. These galaxies challenge our understanding of how galaxies form and evolve. If they are rich in dark matter, why have they not built stars? If they once had stars, where did they go? These dim, silent systems drift through space like the forgotten bones of cosmic history, quiet reminders of the mysteries that remain in the vast universe. Not every galaxy shines with blazing, brilliant light. In fact, many drift silently through the cosmos, unnoticed, their presence barely marked by any glow. Some galaxies remain almost invisible, ghostly islands floating in the vast cosmic ocean, untouched and unanswered by the curious eyes of astronomers. Among the many mysteries of the universe lies a puzzling anomaly known simply as the cold spot. This is found in the cosmic microwave background, the faint, pervasive afterglow of the Big Bang itself. In this enormous patch of the sky, temperatures are unusually low, far colder than the surrounding regions, and it stretches across hundreds of millions of light years, far larger than scientists initially expected. Its mere existence challenges our assumptions about the early universe. Some researchers suggest it may be the sign of a massive cosmic void, a region where matter is astonishingly sparse. Others speculate even more dramatically. Could this frigid expanse be the subtle mark left by a collision between our universe and another during the earliest moments of cosmic inflation? Despite decades of study, no single explanation fully accounts for it. The cold spot is not a glaring, obvious anomaly. It is a quiet, haunting whisper in the fabric of space, a subtle clue that perhaps the universe is far stranger than we imagine. Meanwhile, our very own moon is slowly drifting away from us. Each year, it moves about 3.5 centimeters farther from Earth, roughly the same distance your fingernails grow in that time. This slow, almost imperceptible retreat has been occurring for billions of years, ever since the moon first coalesced around 4.5 billion years ago. At that time, the moon was much closer to Earth, and a single day on our planet lasted just a few short hours. The gradual outward drift is caused by tidal friction. As the moon's gravity tugs on the oceans and Earth spins beneath them, a tiny transfer of energy nudges the moon gently away from us, ever so slowly. It is a quiet, relentless process, invisible in our lifetimes, yet unmistakable across the vast scale of eons. One day, far in the distant future, Earth and Moon may become tidally locked, forever showing the same face to each other, locked in a silent celestial embrace. For now, though, it continues its patient retreat, a steady reminder of the unseen forces quietly shaping our solar system. Binary stars, too, can perform an elegant cosmic dance, exchanging their outer layers as they orbit in close companionship. In certain systems, two stars revolve so near each other that their outer atmospheres begin to touch. Over time, one star may swell, spilling matter onto its companion, creating a delicate, spiraling exchange of material. Sometimes this process is calm and steady, a gentle flow of stellar substance. At other times, the interaction sparks bursts of energy, rapid rotations, or even dramatic mergers, completely transforming the stars involved. The physics governing these interactions is intricate, yet the visual is strangely beautiful. Two stars bound in orbit, brushing against each other, their matter intertwining. One may end up stripped down to a glowing core, while the other becomes swollen and enriched. Their destinies become entwined, linked by gravity, rotation, and the very matter that forms them. Many of the universe's most unusual objects, certain supernovae or compact neutron star pairs, trace their origins back to these quiet, intimate binaries. They are a cosmic reminder that even stars can share, evolve together, and at times, embrace. Even the emptiest stretches of space are never truly empty. Venture far from any star, planet, or galaxy, and you may think you have entered a perfect void. But quantum physics tells a different story. What we call vacuum is actually teeming with activity. Tiny particles and their antiparticles spontaneously blink into existence, only to vanish almost instantly. These constant, ephemeral appearances, known as quantum fluctuations, permeate all of space, providing a restless background to what we often imagine as nothingness. They can subtly influence the movement of particles, modify the behavior of fields, and even contribute to the energy of empty space itself. Some of this activity underpins the mysterious dark energy that drives the accelerating expansion of the universe. So when we picture the cosmos as silent, still, or calm, that image is only partially accurate. Beneath the surface of nothingness, there is a quiet, ceaseless dance of probabilities, a hidden hum of creation and disappearance, forever unfolding just out of sight. Time itself may not flow uniformly across the cosmos. We like to think of time as steady, ticking at the same pace everywhere, for everyone. Yet, according to Einstein's theory of relativity, time is intimately linked to gravity, motion, and the geometry of space itself. Near massive objects, such as black holes or dense clusters of galaxies, time literally slows down relative to regions where gravity is weaker. This is not speculation. It has been experimentally confirmed using satellites, atomic clocks, and precise measurements. Some cosmologists even ponder whether time might vary on even grander scales. Could different regions of the universe experience slightly different flows of time, shaped by the uneven expansion of space in the earliest moments of cosmic history? Though speculative, such ideas hint at a universe where time is not absolute, but fluid, bending and stretching quietly under the influence of gravity and cosmic expansion. Our own Milky Way harbors a hidden component that is far larger than the glowing spiral of stars we see in the night sky. This is the galactic halo, an immense, mostly invisible sphere of diffuse gas, stray stars, and dark matter that extends far beyond the visible edges of the galaxy. Its influence reaches many times farther than the disk itself, playing a crucial role in the galaxy's stability. Ancient star clusters drift within it, and vast unseen mass holds the galaxy together, shaped by billions of years of collisions and mergers. While we cannot see this halo directly, astronomers can infer its presence by studying the motion of stars and the bending of light passing nearby. In truth, the Milky Way is just the luminous heart of a far larger, hidden structure, a glowing center wrapped in invisible arms. Astronomers have recently detected light from a galaxy that existed only 200 million years after the Big Bang. Our universe is 13.8 billion years old, and light, as we know, does not travel instantaneously. It moves through expanding space, its journey stretched and slowed, revealing objects not as they are now, but as they were long ago. The James Webb Space Telescope has allowed scientists to glimpse this tiny, faint, primitive galaxy, a mere infant in the cosmic timeline. Observing it is like peering through a narrow window into a universe we were never meant to see, glimpsing the cosmos in its earliest chapters, when darkness was just beginning to give way to the first glimmers of starlight. On the largest scales, the universe forms a structure that astonishingly resembles a neural network. When astronomers chart the positions of galaxies across billions of light years, they reveal a complex web of interconnected filaments, punctuated by immense voids of emptiness. This cosmic web stretches across the universe like threads connecting distant nodes. When viewed from afar, the pattern eerily mirrors the neural networks in the human brain. Dense clusters of galaxies resemble neurons, while the filaments connecting them mimic the axons linking our thoughts. Of course, this resemblance is purely structural. The universe does not think. Yet, the quiet symmetry between the largest cosmic structures and the architecture inside our own minds is a poetic reminder of the beauty and complexity inherent in nature. Even stars can produce a kind of song. While space itself is a vacuum, devoid of air, stars generate deep, slow vibrations within their gaseous interiors, akin to seismic waves on a planet. These pressure waves cause the stars to pulse, oscillate, and subtly change their brightness. Scientists can detect these tiny variations, using them to peer inside stars in a field known as astroseismology, the seismology of stars. Each star possesses its own unique frequencies, determined by its size, composition, and age. By listening to these vibrations, astronomers can map a star's inner layers, learning about processes hidden beneath its surface. It is a form of cosmic echolocation, a way to hear the secret music of stars across the vast distances of space. Even though the sound is inaudible to human ears, some stars are older than the galaxies that host them. Galaxies are not born in an instant. They grow over billions of years, merging with smaller systems and accreting stars and gas from their surroundings. As a result, some stars predate the formation of the galaxy as we see it today. These ancient stars often reside in the outskirts or in tightly bound globular clusters orbiting far from the galaxy's core. Many of them are over 13 billion years old, nearly as old as the universe itself. They carry chemical signatures from an era when the cosmos was far simpler, composed mainly of hydrogen and helium, with very few heavy elements. These stars are like living fossils, quiet remnants of a universe before galaxies fully coalesced, their light tracing stories older than much of the cosmos around them. Yet, some galaxies appear to defy one of the universe's fundamental rules: the presence of dark matter. Dark matter, the invisible glue that binds galaxies together, explains why stars in the outer regions move faster than expected, and why galaxies cluster the way they do. However, in recent years, astronomers have identified galaxies that seem to contain little or no dark matter at all. Their stars move as if only visible matter exists, challenging conventional models of galaxy formation. Some scientists propose that dark matter could have been stripped away during past cosmic collisions, while others wonder whether our understanding of dark matter is incomplete. Either way, these unusual galaxies remind us that the universe still holds countless secrets, and that even principles we assume to be universal may not apply everywhere. Deep within our own sun, sound waves ripple continuously through the hot plasma, bouncing between layers and causing the star to vibrate in subtle, persistent patterns. These are not sounds like those we hear with our ears. They are pressure waves, slow and deep, far below human perception. Sensitive instruments, however, can detect them, revealing the sun's internal structure in exquisite detail. This field of study is called helioseismology, and it allows scientists to listen to the sun's inner workings, exploring processes otherwise hidden beneath its blazing surface. By carefully observing the sun's subtle vibrations, scientists can probe deep beneath its radiant surface, mapping layers of density, hidden currents of scorching plasma, and complex patterns of rotation invisible to the naked eye. The sun, in this sense, behaves like a gigantic, intricate musical instrument, continuously playing a symphony across millions of kilometers. Its oscillations ripple through its massive interior, revealing secrets about its structure and behavior. With the right instruments, we can listen to this cosmic music, interpreting its rhythms to understand not only the sun itself but also stars scattered throughout the galaxy, each with a unique pulse and resonance, a celestial fingerprint etched in waves of sound we cannot hear. Galaxies are not randomly scattered through the universe. They trace pathways along vast, invisible filaments of dark matter, a mysterious substance we cannot directly see. These filaments, stretching across unimaginable distances, form the backbone of the cosmos. Over billions of years, they have shaped the formation and motion of galaxies, guiding them like beads strung along a delicate thread. Though we cannot observe these filaments with our eyes, astronomers infer their presence by studying how galaxies cluster together and by detecting the subtle bending of light as it passes through regions dominated by dark matter. These cosmic filaments can extend for hundreds of millions of light years, connecting enormous clusters of galaxies, while in the spaces between lie immense voids, regions almost entirely empty of matter. Together, these filaments and voids form a hidden scaffolding, silently guiding the evolution of the visible universe. Yet the true nature of the dark matter forming them remains one of the greatest mysteries in modern astrophysics. Space itself can expand faster than the speed of light, a reality that seems almost impossible at first. Normally, nothing travels faster than light, but these limits do not apply to space itself. In the first fractions of a second after the Big Bang, space expanded at an incredible rate, stretching distant regions faster than light could possibly traverse them. This was not motion through space, but the expansion of space itself. Even today, distant galaxies do not move away from us because they are racing through space. They recede because the fabric of space is stretching. For galaxies far enough away, this expansion causes them to move apart faster than light, forever out of our reach. It is not a violation of physics, but a profound, quiet consequence of how space behaves on cosmic scales. A reminder that the universe does not need to rush. It expands patiently, inexorably, and beyond comprehension. Our solar system, too, is not static. While we often picture planets orbiting the sun in simple, flat circles, the reality is far more intricate. Zooming out, we see the sun itself moving at nearly 1,000,000 kilometers per hour, orbiting the center of the Milky Way. As it travels, the planets follow, tracing a spiraling, helical path through space. The result is a cosmic corkscrew, a twisting ribbon of motion, a vast dance of celestial bodies in constant motion. Nothing in space is still. Planets, stars, and galaxies alike move through invisible currents, drifting along orbits within orbits, spiraling in layers upon layers of cosmic choreography. Even as we sleep, we are moving through these spirals, swept along by the silent, graceful motions of our galaxy. Even the apparent emptiness of space has a temperature. Travel far from stars, planets, and galaxies, and you might think you are entering a void, a region of complete emptiness. Yet even this vacuum possesses a subtle warmth, about 2.7 Kelvin, just a few degrees above absolute zero. This faint glow is the cosmic microwave background, the lingering afterglow of the Big Bang, stretched and cooled over billions of years. It fills every corner of the cosmos, a quiet, omnipresent thermal signature of the universe's fiery origins. Even trillions of years from now, as the universe drifts toward colder and emptier states, this gentle echo of primordial heat will endure, a ghostly reminder of the universe's beginning. At the tiniest scales of reality, quantum fluctuations may have shaped the entire cosmos. Far smaller than atoms, reality is a restless, unpredictable sea. Tiny, random blips in energy appear and disappear in the blink of an eye, a consequence of quantum uncertainty. Many cosmologists believe that during the universe's first moments, these fleeting fluctuations were stretched to enormous proportions through cosmic inflation. Those minute disturbances became the seeds of structure, the very places where matter would gather, galaxies would form, and stars would ignite. In other words, the grand tapestry of the universe, with its vast filaments, voids, and clusters of galaxies, may have emerged from the tiniest tremors in a quantum sea, a reminder that everything we see today began as a whisper of almost nothing. Not all stars end their lives in explosive grandeur. Some die more gently, pulsating as they fade. Variable stars expand and contract, swelling and shrinking in rhythmic cycles that can last days, months, or even years. These pulsations are caused by the star's outer layers alternately heating and cooling, expanding and contracting in a slow, steady heartbeat. These stars serve as cosmic timekeepers. Astronomers have used their rhythmic variations to measure distances across the universe, their pulsing light revealing the true scale of cosmic space. Even in death, stars can mark the passage of time, not with a clock, but with a long, measured breath. Earth itself drifts through a bubble of hot gas known as the local bubble, stretching hundreds of light years in every direction. It is the result of ancient supernovae, massive stars that exploded and sent shock waves through the surrounding medium, clearing out low-density regions. Our solar system floats quietly inside this vast, invisible chamber, shielded by a shell of hotter gas and dust. Though we cannot see it, it is there, a subtle, glowing testament to violent events from billions of years ago, now softened into the quiet backdrop of our galactic neighborhood. Even the most massive structures in the universe can cast empty shadows. Beyond the Great Attractor, a colossal gravitational anomaly pulling entire clusters of galaxies toward it, lies the dipole repeller, an enormous void so empty that it appears to push galaxies away. Stretching hundreds of millions of light years, this void works in tandem with the Great Attractor, creating a cosmic tug-of-war. Together, attraction and emptiness shape the motion of our local universe, a reminder that the presence and absence of matter alike exert a subtle, persistent influence on the dance of galaxies. Right now, trillions of neutrinos pass silently through your body, through Earth, and across the universe. These ghostly particles, produced by the sun, by supernovae, and by the earliest moments of the cosmos, barely interact with matter. Most move straight through planets, people, and detectors without a trace. A few are captured by instruments buried deep underground, offering scientists rare glimpses into their secretive journeys. Neutrinos are everywhere, a silent stream of particles moving at near-light speed, reminding us that even in places that seem still, the universe is alive with motion. The death of massive stars is not always marked by fireworks. The heaviest stars can collapse directly into black holes, bypassing the usual supernova explosion. In these direct collapses, the star's core succumbs to gravity so completely that even the outer layers fall inward without creating a bright explosion. The star simply vanishes, replaced by a dense, invisible black hole. Astronomers have observed stars disappearing as if the light itself blinked out, a reminder that some cosmic endings are quiet, profound, and almost imperceptible whispers into the dark. Galaxies, too, can orbit each other like moons around planets. Many galaxies exist in groups, slowly interacting in dances that last billions of years. The Milky Way has dozens of smaller companion galaxies, including the Large and Small Magellanic Clouds, which trace elliptical orbits around our galaxy. In these celestial interactions, stars can be drawn from smaller galaxies, forming streams and tidal tails stretching millions of light years. Over time, these smaller galaxies may be absorbed entirely, a quiet testament to the slow, graceful evolution of cosmic structures. Some of the universe's most extreme explosions come from magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. When a massive star collapses into a magnetar, it can produce a hypernova, an explosion far brighter than a typical supernova. Such events may generate long-duration gamma-ray bursts, brief flashes of immense energy that can briefly outshine entire galaxies. These bursts last only seconds, yet their light travels billions of light years, a testament to the extraordinary power that can emerge from a tiny, dense star wrapped in magnetic fire. The observable universe has a boundary, but it is not the edge of everything. From Earth, we can see roughly 46 billion light years in any direction. This edge represents the furthest distance from which light has had time to reach us since the Big Bang, not a physical wall or barrier. Beyond it, the universe almost certainly continues, but those regions are moving away so rapidly due to cosmic expansion that their light will never reach us. The universe stretches beyond sight, infinitely vast, quietly unfolding, a cosmos far greater than anything we can hope to observe. Their light will never reach us, not now, and not even if the universe continued forever. The portion of reality we can see is only a tiny bubble carved out by light's limited speed, a spherical window into the cosmic ocean. It's not the true size of the universe, just the slice that has had enough time to send its light our way. Beyond that boundary lies an immeasurable expanse. More galaxies, more stars, and perhaps a never-ending cosmic landscape stretching into the unknown. Some galaxies unleash titanic jets of plasma that fire outward for millions of light years, dwarfing the galaxy that birthed them. At the center of many galaxies sits a supermassive black hole, an object so gravitationally intense it bends the very shape of space. As matter spirals toward this abyss, not all of it is swallowed. Some becomes trapped in twisting magnetic fields and is violently ejected at nearly the speed of light. These narrow beams extend far beyond their host galaxies, forming enormous lobes of radio-emitting plasma that glow across the universe like cosmic beacons. Galaxies with these gigantic jets are known as radio galaxies, and their jets constitute some of the largest physical structures ever discovered. It's one of the universe's great ironies. The most powerful outflows known to science originate from the regions closest to black holes, places where light itself struggles to escape. Even in silence, the universe finds a way to speak. Not every star in the Milky Way follows the cosmic traffic flow. Most stars orbit in the same general direction around the galactic center, like cars on a massive celestial highway. But one peculiar star, known as H04375-439, does the opposite. It travels backward, moving in a retrograde orbit, cutting against the galactic current like a lone swimmer pushing against the tide. Why does it move this way? One explanation is that long ago, it belonged to a smaller galaxy that collided and merged with the Milky Way. Its unusual orbit might be a leftover trace of that long-vanished system. Another possibility is that it was flung into its rebellious trajectory by a gravitational slingshot involving a dense cluster of stars or even a hidden black hole. Regardless of its origin, the star serves as a quiet reminder. Even in a galaxy governed by patterns and physics, some stars choose their own path. The center of our galaxy, strangely enough, contains the chemical signature of raspberries and rum. Sounds like a joke, but the science is real. Astronomers analyzing the chemical makeup of a massive dust cloud near the Milky Way's core discovered ethyl formate, the same molecule responsible for raspberry flavor and the sweet aroma of rum here on Earth. Of course, space itself doesn't smell. The vacuum cannot carry scent like air does, but this discovery reveals a deeper truth. Interstellar clouds are filled with complex organic molecules, alcohols, sugars, and even precursors to amino acids. These are not signs of life, but they are the chemical seeds from which life could one day grow. So while the galaxy doesn't actually smell like a fruit-infused cocktail, the ingredients that produce such aromas drift silently through the void, floating between the stars. One galaxy is slowly drifting toward us, and in a subtle way, it has already begun to touch ours. The Andromeda Galaxy, the closest large galaxy to the Milky Way, is approaching on a slow-motion collision course. Although still around 2.5 million light-years away, the cosmic gap shrinks every second. Meanwhile, the enormous halos of hot gas and dark matter surrounding both galaxies, vast, invisible spheres far larger than the galaxies themselves, are already overlapping. In that sense, the first contact has begun. When the true merger starts roughly 4 billion years from now, it won't resemble a violent crash. Instead, it will be a gradual, elegant intermingling. Stars will glide past each other with enormous distances to spare. Over billions of years, the two spiral galaxies will combine into a single, massive elliptical system, often nicknamed Milkomeda. The process has already been set in motion, a quiet, inevitable rendezvous written into cosmic destiny. All around you right now, even in the empty air of the room you're in, there is a faint glow. This is the cosmic microwave background, the afterglow of the Big Bang. It is the oldest light the universe allows us to see. Around 380,000 years after the universe began, the once blazing plasma cooled enough for atoms to form. That moment freed light to travel across space for the first time. Over billions of years, that ancient radiation stretched into microwaves due to the expansion of space itself. Though invisible to your eyes, sensitive instruments detect it as a near-uniform glow from every direction. A soft whisper from the universe's infancy, still echoing through the cosmos. Supernovae are known for their blinding brilliance, but not every stellar death ends in fireworks. Some stars die in near-total darkness. These events are called failed supernovae. In such cases, a massive star's core collapses under its own gravity, forming a black hole. But instead of exploding outward in a dramatic flash, the outer layers simply fall inward, feeding the newly formed black hole silently. Astronomers have witnessed stars that seemed stable suddenly vanish. No burst of light, no fading embers, just a disappearance. These events hint at collapses so complete that nearly all the energy is swallowed, hidden forever behind the black hole's event horizon. It is a reminder that not all cosmic cataclysms shout. Some occur quietly in the dark. Not every galaxy is a swirling beacon of starlight. Some are almost invisible, faint, ghost-like collections of gas and dark matter with only a sparse scattering of stars. These dim galaxies are difficult to detect with ordinary telescopes, often appearing only as subtle smudges or through indirect gravitational measurements. Some may be failed galaxies, systems that never formed many stars because their gas was stripped away or heated too intensely during early cosmic epochs. Others might simply be transitional stages in galactic evolution. What they all share is a quiet, understated presence. No brilliant spiral arms, no luminous cores, just the silent weight of gravity holding them together. And in the depths of space, even black holes can find companions. When two black holes become locked in orbit, they slowly spiral toward each other, radiating energy in the form of gravitational waves, ripples in the very fabric of space-time. Over time, the orbit decays, and the black holes merge in a final, dramatic moment. No light is produced, yet the collision sends powerful pulses across the universe. Humanity detected such waves for the first time in 2015, confirming one of Einstein's most extraordinary predictions. Since then, we have recorded dozens more. Each one is a distant, invisible symphony of colossal masses colliding in galaxies far beyond our own. As these colossal objects orbit one another, they lose energy in the form of gravitational radiation. With each passing moment, that lost energy steals away some of their orbital momentum, causing them to spiral closer and closer together in a slow, inevitable dance. Over hundreds of millions of years, this gradual inward motion eventually brings the black holes to their final embrace. A moment so brief and violent that space-time itself trembles. When they finally collide, there is no flash of light, no explosion in the traditional sense. Black holes do not shine. Their merger is silent and invisible. Yet the universe still records the moment. The collision unleashes a powerful burst of gravitational waves, ripples in space-time that race outward at the speed of light. On Earth, over 1 billion years later, our detectors tremble ever so slightly when these ripples pass through. The very first of these signals was captured in 2015, confirming a prediction Albert Einstein made roughly a century ago. It was humanity's first direct hearing of the universe, not through light, but through the shifting fabric of reality itself. Since then, scientists have detected dozens more, each one a tiny cosmic fingerprint left behind by massive collisions in galaxies unimaginably far away. These mergers unfold in silence, yet they release more energy in a single moment than all the stars in the observable universe emit combined. Entire suns' worth of mass vanish, converted directly into gravitational waves. For a brief instant, the universe hums. Space-time itself sings a deep, distant note that we can now detect. Not all stars end with a grand explosion. Some die in slow motion, fading gently over billions of years. Stars like our own sun do not go out in a flash. They dim with age. After exhausting the hydrogen in their cores, they swell into enormous red giants, shedding their outer layers into the surrounding space like soft, glowing shells. What remains after this shedding is a dense, hot core called a white dwarf, a stellar ember. It no longer produces energy through fusion. Instead, It simply radiates the leftover heat it once stored, cooling gradually. This cooling process takes an astonishing amount of time, trillions of years for some. Eventually, a white dwarf becomes so cold and faint that it effectively disappears, transforming into what astronomers call a black dwarf. But the universe is still too young. Not enough time has passed for any white dwarf to cool that much. Everyone ever formed is still glowing faintly somewhere in the darkness. Their deaths are quiet and slow, more like embers fading than fireworks bursting. Time behaves strangely near a black hole. According to Einstein's general relativity, gravity doesn't just tug on matter, it warps the flow of time itself. The stronger the gravitational field, the slower time moves relative to regions of weaker gravity. And near a black hole, where the gravitational pull reaches its extreme, this effect becomes dramatic. If you could orbit just outside the event horizon, the boundary beyond which nothing escapes, time would pass differently for you than for someone observing from far away. Minutes spent near the black hole could translate to hours, years, or even centuries for those elsewhere. This isn't science fiction. We've measured the same phenomenon on a much smaller scale using satellites in Earth orbit. Near a black hole, the effect grows immense. They don't just bend space, they stretch time itself. Between galaxies lies a darkness colder than any laboratory on Earth can reproduce. Far from stars, planets, dust clouds, or even stray gas, the intergalactic void reaches temperatures just a few degrees above absolute zero, around 2.7 Kelvin. This frigid cold exists because there is almost nothing there to hold or transfer heat. Only a sparse scattering of lonely atoms drifts through an ocean of emptiness, illuminated only by the faint leftover glow of the Big Bang. These vast stretches of space, sometimes millions of light years across, are the loneliest places we know. Silent, empty, and unimaginably cold. They form the universe's deepest shadows, lit only by the faint whisper of ancient radiation. As the universe ages, it becomes more transparent. In its early years, the cosmos was an opaque fog of charged particles, a thick plasma of electrons and nuclei that scattered light constantly, preventing photons from traveling freely. But as the universe expanded and cooled, electrons paired with nuclei to form neutral atoms. Suddenly, light could move unhindered. This moment, called recombination, occurred about 380,000 years after the Big Bang. It released the earliest light we can observe today, the cosmic microwave background. Since that time, the universe has continued to grow more spacious and more transparent. As galaxies formed and matter spread out, there became less and less material to scatter or block photons. What was once a glowing, opaque fog is now a crystal-clear cosmic expanse where light can travel billions of years uninterrupted. In 2019, humanity captured something once thought impossible, the shadow of a black hole. Using the Event Horizon Telescope, a global network of synchronized observatories, scientists produced the first image of the region surrounding a black hole. Not the black hole itself, but the glowing ring of distorted radiation swirling around it. The black hole resides in the galaxy M87, roughly 53 million light-years away. The image shows a dark, circular silhouette surrounded by a bright, twisted halo of light, evidence of matter swirling at nearly the speed of light under the influence of extreme gravity. It was the result of years of coordination and effort, combining observatories around the world into a virtual Earth-sized lens. More than just a picture, it was a scientific milestone, the first direct glimpse at one of nature's most mysterious objects. You don't need a telescope to see another galaxy. On clear nights in the northern hemisphere, the Andromeda Galaxy appears as a faint, hazy patch of light. That soft glow is an entire galaxy, a trillion stars, more than 2.5 million light-years away. The light reaching your eyes began its journey long before humans existed, crossing the void over millions of years. Andromeda is also slowly moving toward the Milky Way. One day, billions of years from now, the two galaxies will merge, forming a giant new system. For now, it remains a quiet reminder of the vastness of the night sky. You can look up and see something ancient, enormous, and unimaginably distant with nothing but your own eyes. In 2015, A tiny satellite-like detector on Earth picked up the faintest signal ever recorded. A ripple in space-time caused by two black holes colliding more than 1 billion light-years away. The wave stretched and squeezed the Earth by less than the width of a proton. Yet our instruments were sensitive enough to feel it. LIGO and its partner observatories serve as the universe's ears, listening for the deepest, quietest rumbles from distant cosmic events. Each detection is a confirmation of Einstein's prediction that massive objects can send waves through space-time. Even from a small planet in a quiet corner of the cosmos, we can feel the echo of invisible giants merging somewhere far beyond our reach. And finally, some regions of the universe are expanding away from us so rapidly that they are, effectively, lost forever. Because the expansion of space is accelerating, many galaxies are receding faster than the speed at which their light can reach us. Even if we waited for eternity, their photons would never arrive. They are already beyond our cosmic horizon, slipping into permanent darkness as the universe stretches between us faster than light can cross it. As the universe continues expanding, countless galaxies have already crossed a boundary we can never reclaim, a kind of cosmic event horizon. Once an object moves beyond this limit, its light is forever unable to reach us, no matter how long we wait. These galaxies still exist, still evolve, still shine, but from our perspective, they are slipping into permanent darkness. Over billions and billions of years, more of the universe will drift beyond that unreachable edge. The visible universe will not grow. Instead, it will quietly shrink, not because reality is disappearing, but because the light from distant regions will simply never arrive. The cosmos is not only expanding outward, it is also, in a subtle way, letting go of what we can see. Some black holes may be primordial, older than stars themselves. Most black holes form from the violent collapse of massive stars at the ends of their lives. But there is another, far more ancient possibility: black holes that formed in the first tiny fraction of a second after the Big Bang. These are known as primordial black holes, and they would be relics of the universe's earliest moments. In that chaotic environment, minuscule density fluctuations could have crumpled spacetime tightly enough for gravity to form tiny, ultra-compact black holes before atoms, stars, or galaxies existed. These hypothetical black holes could range from microscopic to massive. Some may have evaporated over time. Others may have grown quietly within galaxies. Although we haven't detected one yet, their existence could help solve some of the universe's greatest mysteries: the nature of dark matter, the formation of the first galaxies, and the physics of the earliest cosmic moments. If they exist, they are older than every star, older than every galaxy, ancient fossils from the universe's first heartbeat. Entangled particles may weave together distant corners of the cosmos. Quantum entanglement is one of physics' strangest and most counterintuitive truths. When two particles become entangled, they behave as a single system even when separated by vast distances. Changing one instantly correlates with a change in the other. This doesn't mean information travels faster than light, but it does reveal that at the smallest scales, reality is deeply intertwined, as if space itself is threaded with invisible connections. Some physicists even speculate that entanglement might be fundamental to the structure of spacetime, potentially helping to hold the universe together. If certain particles created shortly after the Big Bang remain entangled today, then the cosmos may contain quantum threads stretched across billions of light years. These connections would be silent, impossible to see, yet present everywhere. Ancient echoes woven through the emptiness between galaxies. Even the vacuum of space has its own kind of pressure. In perfect vacuum, a region with no particles, no atoms, no radiation, you might expect absolute nothingness. But quantum physics says otherwise. The vacuum is actually a restless ocean of tiny fluctuations. Virtual particles flickering into existence and vanishing, fields shifting and trembling at microscopic scales. This activity generates vacuum energy, often linked to the mysterious force called dark energy that is pushing the universe to expand faster and faster. Unlike ordinary matter or radiation, vacuum energy doesn't thin out as space grows. It remains constant, which means the more space there is, the more vacuum energy exists, and the faster the universe expands. It's a strange paradox. The more nothing we create, the more something it becomes. The quiet energy of empty space may be the force slowly tearing the cosmos apart. Black holes also glow, but only faintly and only over unimaginable time. Though black holes are famous for being perfect traps from which nothing escapes, Stephen Hawking discovered that they emit a tiny, ghostly heat known as Hawking radiation. This radiation arises from quantum fluctuations at the edge of the event horizon. Occasionally, one particle escapes outward while its partner falls inward, causing the black hole to lose a tiny bit of mass. Over trillions upon trillions of years, this slow leak of energy can cause a black hole to shrink and eventually evaporate completely. For a black hole with the mass of the Sun, this process would take longer than the current age of the universe multiplied by a trillion. It is the most silent ending imaginable. Not an explosion, but a gradual fade into absolute nothing. The universe contains far more plasma than solid matter. When we think of matter, we imagine solids, liquids, and gases. But the most common state of matter in the cosmos is plasma, a superheated ionized gas where electrons and nuclei drift freely. Plasma flows through stars, fills the solar wind, permeates interstellar and intergalactic space, and stretches across entire galaxy clusters. Nearly all visible matter in the universe exists in this form. Plasma behaves unlike any other state of matter. It conducts electricity, responds to magnetic fields, and can form enormous structures across cosmic distances. On Earth, we encounter plasma only in lightning, fire, and neon lights. But in the universe, plasma is the rule, not the exception. Glowing, swirling, drifting across unimaginable scales. Gravitational waves travel at the speed of light. Gravity doesn't just pull, it can ripple. When massive objects such as black holes or neutron stars collide, they send waves through spacetime itself. These gravitational waves stretch and compress space as they pass, spreading outward like ripples on a cosmic pond. They move at the speed of light, the universal speed limit. Detecting them required decades of engineering and instruments sensitive enough to measure distortions smaller than a proton. Now, with detectors like LIGO and Virgo, we can listen to the cosmos. Each gravitational wave is a message, telling us the mass of the objects involved, how fast they spun, how the merger unfolded, and how spacetime twisted during the event. They are silent to human ears, but measurable, delicate shutters in the universe's deep foundation. The cosmic web connects galaxies across unfathomable distances. If we could observe the universe on its largest scales, we would see a breathtaking structure, a massive network of filaments and voids known as the cosmic web. Galaxies gather along invisible strands of dark matter and gas, forming long, branching patterns that resemble neural networks, spiderwebs, or intricate fractal shapes. Where these filaments intersect, enormous clusters and superclusters form, knots in the cosmic tapestry. In between lie vast, empty voids, regions so sparsely populated they stretch hundreds of millions of light years. You can't see the cosmic web directly with a telescope, but massive sky surveys reveal its structure piece by piece. It is the universe's skeleton, the pattern that underlies everything, a natural architecture grown from gravity and time. The James Webb Space Telescope can see galaxies that no longer exist. The James Webb Space Telescope is not just a camera, it is a time machine. Because light takes time to travel, looking farther into space means looking deeper into the past. When Webb captures images of extremely distant galaxies, it is showing them as they were billions of years ago. Many of them may have merged, evolved, or vanished entirely by now, but their ancient light is still arriving. This creates a strange and beautiful paradox. Webb shows us galaxies that are long gone, preserved only in the light that began its journey before Earth even formed. Astronomy is not the study of what exists now, it is the study of what once existed. Every deep observation is a window into a different era of the universe's history, a gallery of vanished moments still glowing in the dark. Distant galaxies shine with light older than our planet itself. When you look at a galaxy billions of light years away, you're witnessing a moment frozen in cosmic time. The light striking your eyes began its journey long before the Sun, Earth, or the solar system existed. To observe distant galaxies is to look across the ages, to see ancient structures shining with the energy of a universe far younger, far denser, and far more chaotic than the one we inhabit today. The light from that distant galaxy began its journey long before Earth existed, long before the sun ignited, long before the solar system was anything more than scattered dust drifting in a young, chaotic cosmos. Some of the galaxies we observe today released their light over 10 billion years ago, during an era when the universe itself was still forming its first large structures. That ancient glow traveled across expanding space, stretched and reddened by billions of years of cosmic expansion, slowly changing in wavelength as the universe grew around it. And eventually, after an almost unimaginable journey, it reached our telescopes. When we observe that light, we're not seeing the galaxy as it is now, but as it was, a window into a time when the universe was young, turbulent, and freshly shaped. Many of the stars that emitted the photons now reaching us have already died. Some of the structures in those galaxies may have changed, merged, or disappeared entirely. Their light remains, a quiet message from a vanished age, a reminder that the night sky holds stories older than Earth itself. Entire galaxies can disappear behind clouds of cosmic dust. Even something as vast and luminous as a galaxy can be hidden from view. In certain regions of space, enormous clouds of interstellar dust float between us and whatever lies behind them. This dust isn't the kind you find in a house. It's composed of microscopic grains of carbon, silicates, and icy molecules drifting through frigid molecular clouds. When a galaxy lies behind one of these dense regions, much of its visible light becomes blocked or scattered. To uncover these hidden systems, astronomers must look with instruments sensitive to infrared, radio, or X-ray wavelengths, types of light that can slip through the dust more easily than visible light. Using these special tools, scientists have discovered entire galaxies lurking behind areas that once appeared empty. In space, darkness does not always mean absence. Sometimes it simply means waiting for the right wavelength to reveal what's been there all along. Some galaxies wear glowing halos, perfect rings formed by gravity itself. Occasionally, when a foreground galaxy aligns precisely with a more distant one, the gravity of the foreground system bends the light from the background object into a perfect circle. This phenomenon, known as an Einstein ring, is a striking form of gravitational lensing. The galaxy in the foreground acts as a lens, curving spacetime and guiding the background light into a glowing loop. Einstein rings are rare and beautiful cosmic illusions suspended in space, created not through motion but through the geometry of spacetime. The light making the ring may originate from a distant galaxy, an ancient quasar, or even a powerful supernova. These rings allow astronomers to measure the mass of galaxies, map dark matter, and study some of the universe's earliest structures. They are elegant reminders that gravity shapes not just matter, but the very paths light takes. The universe may be infinite, stretching endlessly beyond our reach. When we gaze upward, it is natural to wonder whether the universe has an edge, a boundary where everything ends. Yet current observations suggest that space may extend forever, with no center, no wall, no outer shell. What we can see is limited to the observable universe, a bubble defined by how far light has had time to travel since the Big Bang. Beyond that horizon, the universe may continue indefinitely. If it truly is infinite, then the vast majority of it will always remain unreachable. We will never see all that exists, no matter how advanced our technology becomes or how long we wait. An infinite universe does not guarantee infinite possibilities, but it does promise endlessness. A quiet, incomprehensible vastness with no final border. Cosmic rays strike Earth from deep space every second. Earth is constantly bombarded by high-energy particles known as cosmic rays. Some originate from the sun, but many come from far more distant and powerful events. Supernova explosions, black hole jets, or energetic processes we still don't fully understand. These particles, often protons or atomic nuclei, travel at incredible speeds, approaching the speed of light. Most cosmic rays are diverted by Earth's magnetic field or absorbed by our atmosphere, but some make it all the way to the ground, and a few pass through your body without you ever noticing. They are harmless in small doses, but they are stunning reminders that the universe is not empty. It is alive with motion, energy, and invisible messengers from catastrophic events thousands or millions of light years away. Every once in a while, a cosmic ray hits a detector and silently tells a story that began across the galaxy. There may be no such thing as before the Big Bang. It feels natural to ask what happened before the Big Bang, but according to many cosmological models, that question might not have meaning. In general relativity, time itself begins with the Big Bang. It wasn't just the creation of matter and energy, it was the birth of space and time. Asking what happened before that moment is like asking what lies north of the North Pole. Some theories propose earlier states of the universe, or cycles of expansion and collapse. Others imagine a quantum realm where time behaves differently or may not exist at all. But in many models, the phrase "before the Big Bang" refers to a region of reality where time itself has no definition. The Big Bang wasn't an explosion in space. It was the moment space came into being. Astronomers once mistook quasars for ordinary stars. When quasars were first discovered, they appeared as tiny, star-like points of light. But their behavior made no sense. Their spectra were unusual, and their brightness changed unpredictably. It took years to realize that these mysterious objects were not stars at all. They were the blazing hearts of distant galaxies, powered by supermassive black holes devouring surrounding gas. As matter spirals inward, it heats up to extraordinary temperatures, outshining entire galaxies. Because quasars are so far away, their light takes billions of years to reach us. Yet to early astronomers, they looked like faint nearby stars. What seemed like a simple mistake of identification became one of the most groundbreaking discoveries in cosmic history. Our entire local group of galaxies is drifting toward a hidden mass. The Milky Way does not float motionless in space. Together with the Andromeda Galaxy and dozens of smaller companions, it moves as part of the local group. And this group is not stationary either, it is being pulled toward something far larger, a massive gravitational anomaly known as the Great Attractor. Beyond that lies an even more mysterious region, the Shapley Supercluster, and possibly other enormous structures obscured by the thick plane of our own galaxy. These hidden masses influence the motion of entire clusters, tugging on us with gravity even though we cannot see all of them directly. It's as though the entire cosmic neighborhood is sliding towards something massive and unseen. We don't yet know exactly what lies in that direction, only that we are drifting toward it slowly, drawn in by forces spread across millions of light years. We are living in the universe's stellar springtime. Today, the universe glows with starlight. Stars form, burn, evolve, and explode all around us. But this era of stellar abundance is relatively young. In the first few 100 million years after the Big Bang, the universe was dark, filled with gas but no stars. Eventually, the first stars ignited, illuminating the cosmos and shaping the future of galaxies. Since then, star formation has risen, peaked, and gradually declined. We live in a kind of cosmic spring, a period when stars still form in great numbers but far fewer than in the past. In the distant future, star birth will slow even more. One day, the last stars will ignite, and after that, the universe will gradually dim. But for now, the cosmos is still alive with light, heat, and new beginnings. The universe today is bright enough for us to marvel at it, yet quiet enough for stars to rest in their slow, burning lifetimes. But far into the future, this balance will shift. One day, star formation itself will come to an end. Stars are born from vast reservoirs of cold gas, primarily hydrogen and helium, floating in enormous clouds that collapse under their own gravity. Yet over billions of years, that fuel becomes harder and harder to find. Much of it gets locked inside stars, blasted into space by supernovae, or heated to the point where it can no longer collapse into new suns. Slowly, inevitably, galaxies will run out of the raw materials needed to create stars. As time stretches forward, the brilliant blue giants will vanish first, burning through their fuel rapidly and dying in spectacular explosions. Then the suns, stars like our own, will age, redden, and fade. And finally, the last surviving stars, the dim red dwarfs that burn their fuel with incredible stinginess, will cool into cold, dark remnants. Eventually, the universe will no longer sparkle with starlight. It will dim gradually, gently, like embers fading in a fireplace. What remains will be black holes, white dwarfs, neutron stars, and a cosmos settling into a long, silent stillness. Not tragic, simply peaceful. Most of the matter in the universe is invisible to us. When we look into space, we see glowing stars, swirling galaxies, brilliant nebulae, but these luminous objects account for only a tiny fraction of everything that actually exists. Most of the matter in the universe does not shine at all. It does not emit or reflect light. This mysterious substance is called dark matter, and although we have never detected it directly, its presence is undeniable. Galaxies rotate far faster than their visible mass should allow. Light from distant galaxies bends more severely than expected when passing near massive objects. Clusters of galaxies cling together with a strength that ordinary matter alone can't explain. All of these clues point to a hidden mass, an invisible skeleton of the universe, 5 times more abundant than all the stars and planets combined. Dark matter doesn't glow, but its gravity sculpts the cosmos. It is an unseen framework holding galaxies in place, guiding their evolution in silence. Light from the first galaxies has been stretched by the expansion of the universe. When light travels through space, it doesn't simply move, it changes. As the universe expands, it stretches the very fabric of space, and the light waves passing through it stretch along with it. Photons that left the first galaxies billions of years ago have been elongated into longer wavelengths, transformed from visible light into soft infrared signals. This stretching is known as redshift, and it is one of the most powerful tools astronomers use to measure cosmic distance and time. The farther the galaxy, the more stretched its light. With telescopes like the James Webb Space Telescope, we can finally capture these ancient whispers, light released by the earliest stars, now softened and reddened by the long breath of cosmic expansion. What once shone as brilliant starlight arrives at Earth as a faint, elongated echo, carrying the memories of the universe's earliest chapters. The universe might be a hologram. It sounds impossible, like something pulled from the pages of science fiction, yet some physicists take the idea very seriously. The possibility that our three-dimensional universe might actually be a projection from a deeper two-dimensional reality. This is known as the holographic principle, and it stems from the study of black holes. Evidence suggests that the information describing everything that falls into a black hole is stored not within its volume, but on its surface. If this is true for black holes, then perhaps the entire universe works the same way. What we experience as space, depth, and physical structure could be a kind of mathematical illusion, emerging from information encoded on a distant cosmic boundary. The theory remains unproven, but it is a humbling reminder that reality, even when it feels solid and familiar, may be far stranger and more abstract than it appears. Space may be granular at the smallest scale. To our eyes, space looks smooth and empty. Even with microscopes, it seems like an endless void. But some theories in quantum gravity propose that space itself is not continuous. Instead, it may be made of tiny, indivisible units like pixels in a digital screen, so small that they cannot be divided further. This fundamental scale is known as the Planck length, around 10 superscript 3 meters. At such a scale, smooth space might break down into a jittery, foamy, grain-like structure. We currently lack the tools to see this directly. Yet if space is granular, then everything that happens, every star that forms, every galaxy that spins, every thought in your mind, takes place within a kind of cosmic lattice. Not a perfect void, but a universe with structure all the way down to its deepest level. Some stars spin faster than kitchen blenders. Not all stars rotate gently. Some spin so rapidly that their equators bulge outward, their shapes distorted by overwhelming centrifugal force. Neutron stars, extremely dense remnants of massive stars, take this rotation to an extreme. Certain neutron stars, known as millisecond pulsars, spin hundreds of times per second. That means a sphere of ultradense nuclear matter, only the size of a city, rotates faster than the blades of a high-speed blender. These stars emit narrow beams of radiation that sweep across space like cosmic lighthouses. The pulses arrive with astonishing regularity, so precise that some pulsars rival atomic clocks in their stability. Many of these pulsars orbit close to companion stars, pulling in matter that accelerates them to even greater speeds. They are among the fastest rotators in the universe, ancient clocks ticking in the dark. The universe could end not with fire or collapse, but with a quiet fade. For decades, scientists debated whether the universe would eventually stop expanding and collapse inward, a scenario called the Big Crunch. But evidence now points to a different fate: eternal expansion. As galaxies drift farther apart and star formation slows, the night sky will grow dimmer. Stars will burn out one after another. Black holes will evaporate over unimaginable timescales. Even matter itself may eventually decay. The result is a state known as heat death, a future where the universe becomes increasingly cold and quiet, spreading its remaining energy so thinly that no structures can form. It's not a dramatic ending, but a slow and gentle dissolution. Over trillions upon trillions of years, the cosmos will fade into a whisper, returning to stillness. Some galaxies unleash super winds powerful enough to blow stars away. At the centers of certain galaxies, especially those with intense star formation or actively feeding black holes, enormous winds can erupt. These galactic superwinds push gas, dust, and even newborn stars outward, flinging material tens of thousands of light years into intergalactic space. They're powered by radiation pressure, explosive supernovae, and magnetic fields acting together like a cosmic engine. Over time, these winds can strip a galaxy of its star-forming gas, leaving it red, quiet, and unable to produce new stars. But they also play a crucial role in enriching the cosmos. The heavy elements created in stars, carbon, oxygen, iron, are carried into the broader universe by these winds, becoming the seeds for future stars, planets, and potentially life. A galaxy breathes in its own way, drawing matter inward, igniting it, and then exhaling it back into the void. The far future of the universe is a dark, endless ocean. Trillions of years from now, the universe will be unrecognizable. Galaxies will drift so far apart that each will appear alone in the darkness. New stars will no longer form, and old stars will fade into cold, lightless remnants. White dwarfs will cool into black dwarfs. Black holes will shrink and evaporate. Even atoms may decay, leaving only thin, scattered particles drifting through an empty cosmos. This lonely future is the ultimate stage of heat death, a vast ocean of darkness with no waves, no energy, and no boundaries. Not a sudden ending, but a quiet stillness stretching into eternity. We might be living inside a cosmic void. The large-scale structure of the universe resembles a cosmic web, clusters and filaments of galaxies surrounding massive empty regions called voids. These voids can span hundreds of millions of light years and contain very little matter. Some scientists propose that our own galaxy may lie within such an underdense region. If true, this could help explain strange measurements such as slight variations in the universe's expansion rate. Living inside a void wouldn't affect our day-to-day experience, but it would mean that our cosmic neighborhood is not typical. We might be floating in the quiet interior of a vast, nearly empty bubble, surrounded by distant walls of galaxies held together by gravity. Magnetars have magnetic fields that defy imagination. A magnetar is a special type of neutron star with a magnetic field so strong it exceeds human comprehension. Earth's magnetic field is gentle. It guides compasses and protects us from solar radiation. But a magnetar's magnetic field is trillions of times stronger. Strong enough to distort atoms, shred matter, and erase digital data from thousands of miles away. These magnetic fields fade with time, but while they exist, magnetars unleash powerful bursts and flares of high-energy radiation. A single flare from a magnetar on the far side of the galaxy can be detected on Earth. No human-built laboratory could come close to producing such intensity. Magnetars stand as some of the most extreme, violent, and awe-inspiring objects in the universe. Dense, silent, and wrapped in invisible forces, these cosmic remnants drift like memories made solid, stars reduced to nothing but mass, magnetism, and the faint echoes of what they once were. The universe's largest known structure is a colossal congregation of quasars. In 2013, astronomers uncovered something astonishing: an enormous collection of quasars, the brilliant, energetic hearts of distant galaxies, linked together across an incredible stretch of space. This formation, known as a large quasar group, LQG, spans more than 4 billion light-years, so vast that it strains the limits of our current cosmological theories. According to the standard model of the universe, matter should be relatively smooth and evenly distributed on the grandest scales. Structures above a certain size shouldn't exist, or at least they should be extremely rare. Yet this quasar group blatantly exceeds that theoretical ceiling. It contains dozens of quasars connected in a loose cosmic braid, forming a pattern that suggests the early universe may have been capable of assembling far larger structures than we once believed possible. Whether this enormous system is a true physical megastructure or a statistical coincidence remains debated, but its existence reminds us that the universe is richer, stranger, and more interconnected than our models can always predict. Black holes can warp space into something like a funnel of time. A black hole doesn't just swallow light. It bends space and time into shapes that defy intuition. As you approach the event horizon, the curvature of space-time intensifies dramatically. To an observer watching from a safe distance, time appears to slow down for anything nearing the black hole, the seconds stretching thinner and thinner until they seem to nearly stop at the brink. This distortion forms a gravitational well, a funnel-like structure in space-time where all paths slope inward. Inside, direction loses its usual meaning. Moving forward in time becomes indistinguishable from falling deeper toward the singularity. Space and time blur together, trading roles in a way that is not poetic metaphor, but literal geometry written into the universe by gravity. Some regions of the universe may never meet or ever exchange information again. Because the universe's expansion is accelerating, vast regions of space are already receding from one another faster than the speed of light due to the growth of space itself. This doesn't violate physics. Nothing is moving through space faster than light. Instead, space is stretching between these regions so quickly that light will never bridge the gap. Even if we waited an eternity, the photons from those galaxies would never reach us. Likewise, no signal we send could ever arrive. Over time, more and more of the cosmos will slip beyond our cosmic horizon, isolating each galaxy into its own lonely island of starlight surrounded by an endless sea of dark. The universe is not just expanding, it's quietly fragmenting into unreachable realms. The heaviest element formed in a stellar explosion is gold. Gold is rare not only on Earth, but across the universe. Ordinary stars lack the necessary conditions to forge it. Instead, gold is born in the universe's most violent collisions, when neutron stars crash together or during rare, massive supernovae. In these fiery, catastrophic moments, atomic nuclei are crushed and fused into heavier elements like gold, platinum, and uranium. These newborn atoms are hurled into space, mixing with clouds of gas and dust that will someday form planets. Every gold ring, every tiny flake, every piece of jewelry comes from the heart of a cosmic disaster, an echo of an ancient explosion now resting quietly in human hands. Gold is more than valuable. It is stellar, ancient, and forged in a universe that creates treasure through fire. Space expands while light moves through it. When we observe distant galaxies, we're seeing them as they were long ago. But the light reaching us has also been stretched by the expansion of space itself. As the universe grows, the wavelength of light is pulled like taffy, spreading into longer, redder wavelengths. This phenomenon, cosmological redshift, is one of the clearest ways we measure how far away something is and how much the universe has changed since the moment that light set out. What we see isn't just age or distance, it's history. Light carrying the imprint of every moment space expanded during its journey toward us. Sound waves are frozen into the cosmic structure. Before atoms existed, the universe was a dense, hot plasma where light could not travel freely. In that early era, pressure and gravity created rippling waves, acoustic oscillations, similar to sound waves traveling through air. These waves left imprints in the density of matter, like frozen echoes. Today, this ancient sound survives in the arrangement of galaxies, a subtle preference for certain distances between them, a standing wave preserved over billions of years. This relic, called baryon acoustic oscillation, is a fossilized whisper from the universe's youth, an imprint of cosmic sound that still shapes the large-scale structure of everything we see. Galaxies can be eaten by larger ones without leaving a trace. Galaxies rarely live peaceful lives. Over billions of years, they interact, collide, and merge. When a smaller galaxy drifts too close to a larger one, the bigger galaxy's gravity can slowly tear it apart. Its stars stretch into elongated streams, wrap into spirals, and eventually blend seamlessly into the larger galaxy's halo. We see these stellar streams around the Milky Way today, ghostly trails of stars that once belonged to smaller galaxies long gone. This quiet process, galactic cannibalism, is not violent in the explosive sense. It is slow, graceful, and inevitable. Big galaxies grow by consuming the small. Some stars flicker with rhythms like cosmic fireflies. Not all stars shine steadily. Many pulse, dim, or brighten in repeating patterns. These variable stars change because of internal processes. Pressure waves moving through their layers, eruptions on their surfaces, or eclipses from companion stars. Some flicker in hours, others take years. These variations are so consistent that they serve as cosmic measuring sticks. By studying their flickering patterns, astronomers can calculate distances across vast stretches of space. Stars don't simply burn, they pulse with cosmic breath. Some black holes roam the universe alone. Not every black hole sits anchored at a galaxy's center. Some wander freely. They can be ejected during galactic collisions, flung outward by gravitational encounters, or kicked loose during the merger of smaller black holes. These rogue black holes drift through space in silence, nearly impossible to detect unless they happen to pass through clouds of gas or tug on nearby stars. They are cosmic exiles, massive, invisible travelers with no orbit, no companion, no home. Even black holes can be launched across galaxies by their own collisions. When two black holes merge, the gravitational waves they release don't always burst out symmetrically. If more energy is radiated in one direction, the newly formed black hole recoils, like a cannon firing with nothing to anchor it. These kicks can reach thousands of kilometers per second, fast enough to fling a black hole out of its host galaxy entirely. The universe's heaviest objects, often anchored at galactic centers, can be thrown into intergalactic space by nothing more than the memory of their own merging shock. Some stars end as crystallized cores, giant cosmic diamonds. When a star similar to the Sun dies, it sheds its outer layers and leaves behind a hot, dense core called a white dwarf. Some white dwarfs are mostly carbon, and under their immense gravity, that carbon begins to crystallize. Over billions of years, they become vast stellar diamonds, Earth-sized gems glowing faintly with leftover heat. Astronomers have even detected pulsations from some white dwarfs, like a ringing bell made of crystal. Once a shining star, now a cold jewel drifting through space, a monument to an ancient fire. Most of the universe's history hasn't happened yet. Though the universe is 13.8 billion years old, this is only the opening chapter of a story trillions of years long. Stars are still forming. Galaxies are still changing. Cosmic evolution is in its vibrant youth. Nearly all of the universe's future, its quiet eras, its fading light, its slow transformations, still lies ahead. We are living at the dawn of time, not its end. Black holes, despite being the darkest objects in the universe, still glow, not with their own light, but with the furious heat of matter spiraling toward them. Even now, as you listen, countless tons of gas are falling into these gravitational abysses, heating to millions of degrees, radiating brilliant X-rays before crossing the point of no return. In the unimaginably distant future, this glow will fade. Stars will extinguish one by one. Galaxies will drift apart like lanterns carried down a widening river, and the cosmos will cool into a quiet, shadowed expanse where almost nothing happens. But that era belongs to a time trillions of years ahead. We are alive during a luminous chapter, a golden intermission when stars still burn, galaxies still dance, and the universe still hums with motion and change. The past is enormous, but the future is vastly larger. Supernova remnants continue growing for thousands of years. When a massive star reaches the end of its life, it detonates in a supernova, an eruption so bright it can eclipse an entire galaxy for a moment. Yet the explosion itself is only the beginning. The shock wave expands outward for centuries, carving a growing sphere into the surrounding space. It sweeps up dust, hydrogen clouds, and even the remnants of older stellar deaths. These expanding bubbles of debris, supernova remnants, glow across the spectrum. In radio waves, X-rays, visible light, ultraviolet arcs. Their shapes vary from delicate webs of gas to roiling storms of turbulent knots. The Crab Nebula, still expanding from an explosion witnessed on Earth in 1054 CE, is one such relic, a star's long exhale, still unfolding almost 1,000 years later. A distant star's light can be twisted by nothing more than a passing planet. We ordinarily think of gravitational lensing as something done by massive structures, galaxies, clusters, black holes. But even a planet cold, dark, insignificant in comparison can bend starlight. When a planet drifts directly between Earth and a faraway star, it acts as a tiny lens. The effect is subtle, called microlensing, but powerful enough to reveal planets we cannot otherwise see. Even planets in other galaxies. A small flicker, a gentle rise and fall in a star's brightness, and suddenly, an unseen world whispers, "I'm here." There was once a time when the universe glowed a brilliant orange. In the early epochs after the Big Bang, the cosmos was a blazing plasma, thick, hot, shining. As it expanded and cooled, the glow shifted, and when the temperature dropped to around 3000 Kelvin, matter transitioned. Electrons settled into atoms. Light was freed. In that moment, the universe would have appeared as a warm, orange radiance filling all of space. No stars, no darkness, only a uniform cosmic glow. That ancient light has been stretched by expanding space into the faint microwave background we detect today. A whisper of warmth, a fossil glow. But long ago, the cosmos looked like a burning ember cooling into night. Some parts of the universe cool more slowly than others. The cosmic temperature falls gently as space expands, like an oven gradually shutting down. But not all regions cool evenly. Dense pockets of matter, clusters of galaxies, and areas rich with hot gas remain warm for billions of years. Other regions, sparse, empty, lonely, cool much faster. These subtle differences shape everything. How stars form, how galaxies grow, how long cosmic structures survive. The universe doesn't cool like a machine. It cools like weather, uneven, patchy, textured, alive with local variation. One day, we might witness the birth of an entirely new universe. Some cosmological theories suggest that new universes could bud from our own, through quantum fluctuations, through the collapse of black holes, or through mechanisms we have not yet dreamed of. If such a birth occurred, it would likely begin far beyond our observational reach, a tiny bubble of new physics expanding uncontrollably. We don't know if this has happened before. We don't know if it will happen again. But the idea remains. Within the quiet darkness of our cosmos, a new creation could begin. A universe born inside another's fading warmth. The cosmos is still ringing from its earliest instant. In the first fraction of a second after the Big Bang, the universe ballooned outward in a burst of expansion called inflation. That explosive stretching froze tiny quantum fluctuations into enormous cosmic structures. These ripples seeded galaxies, stars, planets, everything. The universe carries these imprints. We see them as temperature variations in the cosmic microwave background. We may someday detect them directly as primordial gravitational waves, faint tremors of space-time itself, still resonating from the universe's birth. The cosmos appears silent now, but deep within it, the first vibration is still humming, like a bell that has never fully stopped ringing. You are a way for the universe to know itself. Of all the strange truths in astronomy, perhaps the most beautiful is this: you are made of ancient stars. The carbon in your cells, the oxygen you breathe, the iron flowing in your blood, all of it was forged in stars, scattered across galaxies, and eventually woven into living beings. You are not separate from the universe. You are a small piece of it waking up, realizing itself, wondering about itself. Through you, the cosmos looks back at its own vastness. Through your thoughts, it contemplates its own origins. Through your dreams, it imagines what might come next. Now, as you drift towards sleep, the universe continues dreaming through you. Thank you for traveling with me tonight through distant galaxies and dying stars, through cosmic echoes and expanding space, through the great, ancient quiet that surrounds us. We've journeyed across billions of years, listened to the faint music of creation, and found ourselves resting gently in the starlight. Somewhere in all of this, in the glow of old stars, in the hush between galaxies, in the soft shimmer of drifting dust, there was you, breathing slowly, thoughts softening, maybe already drifting into dreams. The universe is full of motion and fire, but also deep stillness, contains chaos and collapse, but also peace. And the fact that we can understand even a tiny part of it, piece by piece, moment by moment, is something quietly miraculous. So, wherever you are right now, whether fully awake or floating just beyond the edge of consciousness, may your dreams be gentle. May your body rest like starlight settling on calm water. And may you carry with you the faint memory of a universe that glows, not only above you, but within you. If you're still awake, feel free to watch the next chapter. And if you'd like more softly told stories filled with wonder and cosmic quiet, consider subscribing. There is always more to explore, one peaceful mind at a time. Good night.